You know what's interesting about an instrument error? Some of them you can see coming. A bad connection, a blown fuse, a sensor that's just dead. Those are obvious. You fix them and move on. But there is one type of error that's sneaky. It doesn't announce itself. It just slowly creeps in, day after day, until one morning you are looking at a reading and thinking, wait, that doesn't seem right. And the frustrating part, the instrument isn't broken. It just drifted. That's what this lesson is about. Drift. So let's define it properly. Drift is a slow, undesired change in an instrument's output over time, without any change in the actual input. Read that again. The input hasn't changed. The process hasn't changed. But the instrument is reporting something different than it should be. That word slow is doing a lot of work in the definition. This isn't a spike. It's not a sudden jump. It's a gradual shift. So gradual, in fact, that it often goes completely unnoticed until calibration time. Think of it like a clock that loses 2 seconds every day. On day 1, you had never noticed. After a year, you are 12 minutes behind and wondering why you keep missing your meetings. Same idea here. Let me walk you through the classic example on your slide. You have got a temperature transmitter. You just calibrated it. Everything is perfect. At 100 degrees Celsius, it reads exactly 100. Clean, accurate, done. Now, fast forward 6 months. Nothing has changed in the process. The temperature is still sitting at 100 degrees Celsius. But the transmitter, it's now reporting 102. 2 degrees, that's a drift of 2 degrees over 6 months. Now, is that a crisis? Depends on your application. In some processes, 2 degrees is completely acceptable. In others, like pharmaceutical production, precision chemical reactions, that 2-degree error could cause real problems. The point isn't the size of the drift. The point is that it happens silently, without any alarm, without any obvious failure. That's what makes drift so important to understand and to manage. So, what's actually causing this? The slide lists the main culprits, and they are worth going through one by one. Component aging. This is a big one. Every electronic component has a lifespan, and as it ages, its characteristics change slightly. Resistors drift, capacitors drift, reference voltage drift. It's just physics. Corrosion. Especially relevant in harsh industrial environments. When process fluids, moisture, or chemicals attack sensor materials or electrical connections, you get signal error that build up over time. Dirt build up. Mechanical sensors, diaphragms, pressure taps, if they get coated in process material, their response changes. And environmental factors. Temperature swings, vibration, humidity, all of these stress the instrument in ways that gradually shift its calibration. None of these happen overnight. That's the nature of drift. Here's something I want you to hold on to from this lesson, and it's captured in that quote on your slide. Drift is why scheduled calibrations exist. It's not that we calibrate instruments because we expect them to break. It's because we know with certainty that over time, every instrument drifts to some degree. The question isn't if, it's how much and how fast. When you go into calibrate an instrument and you find it's 2% off, that's not a failure. That's the system working exactly as intended. You called the drift. You corrected it. You sent it back out accurate. And here is something worth knowing for when you are reading datasheets. Manufacturers will often specify drift rate something like plus minus 0.1% of span per year. That number tells you how fast you can expect the instrument to drift under normal conditions. It directly informs you how often you should be calibrating it. Longer drift spec? Maybe annual calibration is fine. Tighter application? You might be on quarterly schedule. So let's quickly recap what we covered. Drift is a slow, undesired shift in an instrument's output that happens over time, even when the input is perfectly stable. It's caused by aging, corrosion, contamination, and environmental stress. It's invisible until you look for it. And it's the primary reason we have planned, scheduled calibration programs in any serious instrumentation setup. In the next lesson, we are going to look at another important instrument characteristic, one that deals with how an instrument responds when you change the input and then change it back. Stick around. See you.